Okay, so we'll get started. So again, yeah, hi, I'm Collen Bertoni. So this talk will be about math libraries and also how to find them, how to link them in, and then some debugging tips. So not super into the details about exactly how to use math libraries, but more if how to find them, use them, and then if you encounter issues, what possibly you can do. Okay, so in particular, I'm going to do a quick getting started section. I know some of this was covered earlier, but I just want to be clear how it's affecting linking in libraries, what maybe is already there by default and what isn't. Then I'll go over available math libraries and how to look for them in the system. Then some sanity checking strategies, just for checking like if the libraries you think you linked in are actually there, just if you see something acting as you don't think it should, here are some sanity checking tips. And then a short debugging game is just examples of common problems that people have run into in the past or sent to support at ALCF that you maybe encounter and what possible fixes are. So getting started. So this is just overview of things with a view to linking in libraries. So again, this comes to modules. So like I think all of you know, like Marta mentioned, environments are handled by the environment in Aurora is handled by modules. So importantly, these set things like the path, include path, LD library path, which is where when you're running and compiling, it will search for libraries. So the modules you have loaded can affect what libraries you're linking to. So generally, we recommend always checking with module list when you run and also when you compile, just to make sure you have the same environment loaded at both times. Module right now looks like what you would see above. And you can just have that in run script and compile script and then compare. And again, I know we've mentioned this before, but Aurora uses MPI compiler wrappers. So the Intel compilers under the hood are ICPX, ICX, and IFX. And then MPI CXX, MPI CC, MPI iFort, or MPI F90 are the wrappers. So these, when you compile, it links in extra libraries from mpitch. So usually you can compile with like -v and get a huge output and see what all it's linking in. But usually MPI CXX or any of the other MPI wrappers with -show will tell you exactly what you're linking in. So that can be useful to see if you're not sure what the MPI exec's libraries are linking in. It does so, yeah, pulls in mpitch by default. Some systems their compiler wrappers will pull in math libraries also by default, but here it doesn't do it. So you'll need to link those in with library names and paths. So most of the libraries and other environment variables, like I mentioned, are managed by modules. But the really important point I want to make is most of the libraries you get will be done via dynamic linking. So this is important because what it means is that at runtime, it searches for the library routines. It won't pull them in at compile time. So you should make sure that the environment you compile with matches that you run in, because if you compile with a library that's around at compile time and then you run, you might get an error saying, I can't find this exact version of the .so. And then if there's a machine upgrade or something and one of the older libraries is deleted, you try to rerun and it won't be there. So it's important to know that most of them are done by dynamic linking and you should be aware of that. There are some ways around this, like static linking pulls the library symbols into your object at compile time, so then you wouldn't have this issue of having a difference between compile and runtime. Also, some of the libraries, like for example, mpitch, like we saw above, it adds in the libraries. They're still shared libraries, but it links them in with our path. So if you change the module you have loaded, which changes the environment, it will still use the same mpitch you compiled with because it's telling it at compile time, always use this exact path. So in some cases, if you load a different environment, you might use a different library. But in the case of others, if they were compiled with our path or statically, you would use the same library that you compiled with. And then you can always compile with -v to see the exact like all the exact things that are being linked in and compiled with at compile time, so you can confirm that way. And just again, the modules are the things that are setting the environment. It's not black magic at all. You can just do like, for example, for Petsy, you would load modulo Petsy, but if you do module show Petsy, you can see exactly all the library path, LD library path includes, so on, that's adding. So you can, all it does is set the environment. So you can, if you really wanted to, you could just take these and do them by yourself in a bash script or something. So you can always, if you think you're linking something, you don't understand why, you can always go look at what the modules are actually doing. So with that, just like the general getting started, so available math libraries. So the main available math library is Intel's 1MKL. This is I guess the default in the system because it's an Intel system. I'll talk about this, some more examples of this in the next slides, but before, there are also a long list of non-Intel provided libraries. You can see many of these with module avail. So I'm not going to go through all of them because it's really non-exhaustive. So I would suggest doing, module avail and then see if the library you need is there. So just stuff I think a lot of people are already familiar with, like Boost, Amrex. For FFTs, Intel has another version of libraries for FFTs, so we have that installed. You can take a look. Hefty, Hyper, Petsy, SuperLU, Netlib's version of SkillApack. So there's a lot there. Then I'll talk a little more going to depth in Intel's 1MKL because that's our main math library. So this used to be, I think probably most people are familiar, Intel had MKL or math kernel library for a very long time. 1MKL is just kind of the rebranded plus GPU support version of MKL. It's loaded by default in the 1API module. It's not linked in by default, but a lot of the environment variables needed are there. So the main one is the MKL root environment variable. So if you echo a $MKL root, you can see where the root of MKL is. And if you go in /lib, you can see all the different libraries that MKL has available for you. If you're familiar with MKL, it's basically the same as in regular MKL, BLAS, LAPACK, FFT, sparse linear algebra, vector math, and so on. These links at the bottom from Intel have the more exhaustive list of all of the functions that are available. It has API support for C, C++, Fortran with 64 and 32-bit interfaces. It has a lot of different support for a lot of different data types, including some of the lower precision, like FP16, bfloat16, and TensorFlow 32 on the GPU. So if you're interested in lower precision, there are some MKL routines you can use. For the CPU side, these are just unchanged from regular MKL. You can still just link and use just regular APIs for BLAS and LAPACK. The GPU APIs are in SYCL or OpenMP offload. And if you want to see examples of that, the thing that you can go, like the website has some examples, but personally I like looking at code that's on the system. So if you go to, I already put the slides in Slack, but if you go to MKL roots, share doc MKL examples, there are a lot of tarballs with examples for the different APIs. So the SYCL API, the OpenMP offload, Fortran API, the C OpenMP offload API, and then just CPU APIs, like that's the core so CPU side for Fortran C, Fortran 95. So you can copy these to your directory, untar if you're interested in like the Fortran OpenMP offload examples, and then you can take a look at, so if you go into just F offload, there will be like BLAS, LAPACK, and so on. And I just picked I picked LAPACK and source, and for a variety of different MKL functions, you can see these very small examples just to get an idea of how things are structured. So I find that that's usually what I've done in the past to see. So once you have found examples and you know how to write your code, the next thing is just how to build it. So there are kind of two big ways of doing it from 1MKL. either link line advisor. This is if you are like compiling on the command line using a makefile or using just a bash script or some other type of script that I know some of the applications I've worked with use. For this, the link line advisor, which I put a link to here, is really essential. Here, it's just a website, and you put in what compiler you're using, architecture, how to link, what the interface is. So interface would be like DB++ or OpenMP offload, what type of CPU side threading, and then what domain, so sparse, and then it will output a line to use to link and a line to use to compile with. Often, and that's like the 100% Intel recommended way of doing it. Often, if you just want to get things working quickly in chest, you can just use -qmkl, and a lot of the time that will just link in things correctly. But the official way is go grab the link line and the compile line. They also have CMake support. So the link here has the Intel's version, or like comments from Intel about how to use their CMake. If you want to take a look, it's under mkl root lib cmake mkl config.cmake. And if you take a look at that config file up at the top, it will tell you, it has some useful information about how to link in libraries. So you typically do it here with the target link options, whatever your target is, probably public, and then what you want to link in. So mkl : mkl is just the CPU side, C and Fortran API. mkl sickle is a link line for sickle API, scale pack box, and so on. And I just cut it off here. So this is useful if you are working with a CMake project. I think I have, yeah, just for the tiny example, a CMake list.txt, you would find package mkl, add your executables of the project, just some app.cpp or app.c, and then target link libraries, your application, and then mkl. So just a simple example. Sometimes the CMake isn't flexible enough, and I know some people sometimes have to go back to putting in the explicit path, but this is worth a try if you are using CMake. And then, okay, so hopefully that's enough, some examples of where you can look for examples to get started, and then linking, so some sanity checking. So like I mentioned before, most libraries are linked in via dynamic linking. And so that means, again, it's really, really useful to check your environment at compile and runtime to see what shared objects or shared libraries you're linking in. So you can do that with LDD. So for my application games, I LDD games, and then I can see I'm linking in sicklebloss.so.5, and it's coming from this location. I'm linking in libmpi, and it's coming from this exact location. It's not a different mpitch. And maybe this is the mpitch I mean to use. So it's really, LDD is useful to tell you what libraries you're linking in and also where it's pulling them from. You can also do this just for a pure single basis. So maybe I possibly had two libraries that were implementing dgem. So you can ask the linker where they're getting, what library they're filling in that object from. So you can ask for the symbol name, like you can ask the linker with -wl, -y and the symbol name. So here I'm asking in my application, where is dgem? And I see it will output a bunch of text, but it will say, okay, I have a reference to dgem in this, which is just an object from the code. And then it will say, the linker will say, the definition of dgem that I'm pulling in is from libmkl Intel ILP64 to SO. And that can be useful because I think, like I mentioned before, MKL has both ILP64 64-bit integer interfaces and LP64 32-bit interfaces. So it can be useful to, if you want to just double check where your symbols are coming from. The other thing is MKL has a tracer. So if you set MKL for both equals 2, you can see a trace. As you're running, it will give out a trace of what MKL calls you're doing, what sizes, basically just the, when you do the call, what variables you're passing in. There's a lot of information at this link. There are some restrictions on which calls will show up. Some of them don't have the MKL verbose implemented, so they won't show up, but many of them do. It will output a lot, especially if you're doing a long run. So there's a nice summary tool from Thomas, which will take in all the output and give like a summary table. But what this looks like is, so running the test, so running a code with MKL verbose equals 2, so running tests on GPU, running with double precision real data type is all output from the program. And then all of the output from MKL verbose will start with MKL verbose. So it just does, the first time it starts, it does some output, just general about the system. And then what you see is like here, MKL verbose, you're calling dot, the MKL, the BLOS dot function, double precision, and then like a pointer to your array, then the size of the array. This is just the regular function signature from dot. So you can like double check the sizes and if the addresses look normal, things like that. Also, it will tell you if you're running on GPU and how long they take. However, MKL verbose equals 2 to do the tracing, it makes everything synchronous, so it might take longer and be not exactly what you're doing when you're running for real, because maybe you're not doing all of that synchronously. But it's, yeah, very useful. And then, of course, for other sanity checking, yeah, please reach out to ALCF support if you find any issues, or for this hackathon on Slack. Okay, so last thing was the debugging game. It's just a set of examples. So you can, as I go through, if you want to think in your head how to resolve them as we go through, but I'll just go through. These are like common library-related issues people have had in the past. Okay, so first I'm going undefined reference error. I'm going along, I use my makefile to compile, things seem okay, but then I get a bunch of undefined reference errors. So as I'm running, it says, yeah, mathlib.f has undefined reference to dgem, another undefined reference to dyssm, one to ddot, etc. So undefined reference error is somewhat common. Usually this means that there's a library missing at link time. So either a -l library, like the path of the library you need is missing, or the module isn't loaded because that module was loading something into the library path, or a flag is missing. So in this case, we were just missing linking in a BLOS library. So this can be resolved by rebuilding with the path to the math library. So again, for my OpenMP offload code, if I go to linkline advisor, I get the long fsicle lib until 64, so on. Or like in this case, -qmkl is okay too, but again, yeah, we recommend linkline advisor. This can also come up with linkline advisor if instead of grabbing the link line to compile with, you only grab the compiler option. So just a reminder, if you're using this tool, to grab both the link and the compiler options. Okay, number 2. So we were able to compile fine and then try to run. We just have a regular job script. You sort of saw this before, MPI exec. We're running on a single node, 24 ranks per node. We use a CPU bind depth of 8, and the nice GPU tile compact script to get our ranks on the GPUs we want. But we try to run and we get this error while loading shared libraries error. libmpi.soda12 can open shared object file, no source file or directory. So this is another common one, runtime can't open shared object file. So what was the issue? The issue was I didn't set the modules correctly at runtime, so I can check with LDD, the executable, to see, okay, now in my runtime environment, it is not finding MPI. So the solution was just to load the needed module for mpitch or do a module restore to get back to the original environment. That's often, if you think you've messed up your environment, module restore will help restore it. Then the last one, so we're compiling okay, we're running okay, at least getting beyond the initial error, but there's a strange runtime error about MKL parameters. So say running here and I get an Intel 1 MKL error, parameter 1 was incorrect on entry to DGESV, so it's a LU decomposition. So yeah, that's been seen by multiple people before. So what's the issue? Well, we can read it until, or MKL thinks there's a problem with an input parameter. So one nice thing we can do is use MKL verbose equals 2 to look through what it thinks the parameters are. So running with mklveros equals 2, we get the error, parameter 1 was incorrect, and we can see what mklveros was getting. So we see the function call. So this is a CPU call. We get a crazy large number as our first input, and then some other numbers and other addresses. So we can just go look at the API. And here we were calling the Fortran API, so it's an address. We know it's a pointer, but it's an address. So what was the problem here? The problem was we were linking to the 32-bit interface when we needed to link with the 64-bit interface. This is really only important if you're using integer pointers for things. So by default, QMKL is linking in the 64-bit version, but if you're sending it pointers to 32-bit integers, make sure you're linking to the correct MKL version. And we're happy to talk about that more if you run into issues with that. So summary, but yeah, we use compiler wrappers. So some libraries like mpitch are linked in by default. If you want to see available modules, module avail is good. Important to do sandy checks like LDD on your executable to see what's linked in and to check compile versus runtime. Also, yeah, and if you can always use ALCF support as your sanity check too. So you can email us or ask us on Slack and we will help with sanity checking too. So one last extra debugging tool. This is a little bit new to Aurora. So it's sort of a new linter for Fortran. It will analyze your code line by line to look for issues with correctness, modernization, or security and optimization. Mostly what we've had people use this for at Aurora in the past is modernization. So if you run it, it will go and say, oh, you're using implicit none, and mark it down, and you end up with a list of all the places where it thinks, or where the code is using like old versions, or maybe like new specific extensions, things like that. It can be, there are some auto-correcting, but often it's still just useful to have a list of things to look at and possibly fix in the future. It's available with module use, soft module files, module load Cody. There are quick starts in the docs, code.cody.com. And we've worked with this company before, so if you have issues, if you have a Fortran code, it's possibly worth trying, and let us know if you have any issues. And that's all I have, so thank you.